Now let's look at this problem. In this problem, as you can see, we have a spherical raindrop in here with radius r, and we have light incident from air and strikes to this raindrop and creates a 60 degree of incidence angle. But as you can see in the question, we have two different refractive indices for two different colors, for red and violet in here. To understand the logic of this problem, we need to be familiar with some phenomenon called dispersion. I will briefly talk about the dispersion concept. If a material or an optical element is dispersive, then that element focuses different wavelengths on different positions in space. The most common example is, as you know, probably, is prism. If white light strikes a prism, the prism would separate the white light, the polychromatic light, into its component wavelengths, and each component would focus on a different positions in space. And the reason behind this is that because each component would experience a different refractive index for the same material. So for each wavelength, we will have a different refractive index. The logic of this problem is this. We have two different wavelengths given in here, red and violet, and this raindrop will have different indices for the two wavelengths. Okay, now the question actually asks for the difference between deflections of red wavelength and violet wavelength. And we will do the calculations in general. Then we will insert these different indices and find the difference between deflections. Okay, our starting point is again Snell's law. I will write Snell's law for the first refraction interface from air to raindrop. I will say sine 60, 1 times sine 60, but I will not write the refractive index of air, n times sine theta 1. As you can see, I made this angle as theta 1, and since these are both r, these lengths are both r, this angle will also be theta 1. Okay, I will use this in a minute. Now, for sine theta 1, I can say that it will be equal to sine 60 over n. Okay, now I will use the second angle. On the second refraction in here, theta 1 is incidence angle, as you can see. Then I will say that n times sine theta 1 will be equal to 1 times sine alpha. As you can see, this green angle is the refraction angle, alpha. So if I substitute this sine theta 1 value, I see that sine alpha will be equal to n times sine 60 over n, and alpha will be equal to 60 degrees. Okay, now I need to do some geometrical tricks. Actually, this is not actually a trick, but I need to do some arrangements. As you know, if we didn't have any different medium in here, if we didn't have any raindrop in here, our light wouldn't be refracted. It would just go straight forward, and we wouldn't have a refraction angle. But now we have a refraction angle theta 1, and we have a deflection angle alpha 1. So I will try to find alpha 1, but it's easy. If there weren't any deflection, then this total angle would be 60 degrees. Then I can say that actually theta 1 plus alpha 1 will be equal to 60 degrees, and alpha 1 will be equal to 60 minus theta 1. Okay, now on the second refraction point, as you can see in here, our deflection occurs in here. Actually, not exactly in here, but we are trying to find this total deflection. So our deflection phi will be equal to alpha 1 plus alpha 2. Then we need to find this alpha 2. If you look at here on this X shape, we can see that this angle is theta 1, as I wrote here. But in general, this angle is alpha that I found in here, 60 degrees. So I say that alpha, which is 60 degrees, will be equal to theta 1 plus alpha 2. This extra angle is alpha 2. The deflection angle is alpha 2. Then I can say that alpha 2 will be equal to 60 minus theta 1. Now to find phi, the deflection, the total deflection angle, I will just substitute alpha 1 and alpha 2 values, which will give 120 minus 2 times theta 1. Okay. Now I know that theta 1 from here, theta 1 actually is equal to arc sine 60 over n. Then I will substitute this in here. I say my phi is 120 minus 2 times arc sine 60 over n. Now, this is my final calculations. At this point, I need to insert the different n values for different wavelengths as given in here. And then I will finalize my calculation. I will find my final solution. Then I say phi 1, phi red, let's say, 122 times sine, let's say sine minus 1, sine 60 over the refractive index given for red is 1.330, and phi violet similarly will be 9 minus sine 60 over 1.1341. Okay, if I calculate this, actually I will simply subtract them. As you can see, the violet value will be higher than the red value. So I will write this, but it doesn't matter. We can put this in here. And if I do all the calculations, I mean the calculations in here, I will find 0.80 degrees. So what I see in here is if a polychromatic light incidence to a raindrop, it will disperse into two different wavelengths, and one will focus on here, one will focus on here, because one of them will experience 1.33 refractive index of 1.33, and the other one will experience 1.341 in here.